Hello and welcome. So here we are in lecture 10. This is the front slide from lecture 9. So yes, we're going to start off by finishing off the topic from last time. And then we're going to shift gears. So remember from last time we were talking about testing. And we tried to extol a number of virtues, mostly just you should be excited about testing, see it's something you do continuously throughout the design process and implementation process, not just at the end. Consider it testing when you're designing your project in the first time to think about how can I make this easier to test. And we talked about when you're testing, there's kind of three main things. You got to have test cases, which are both somehow input, somebody know what the right output is, and somebody kind of script it all together. And so we saw some examples where we, use either simple human-generated input tests or actually use, exhaustive testing or random testing. And we did that in combinational circuits. We also scripted together ways to do the interactions in the testing. And so today, let's talk about the sequential component. How do we do something that has state in it? So to cover that, we're going to do a queue. So I started this last time. I'm going to start over from the beginning again this time. And so the challenge for testing a stateful component is not just about testing the current inputs, it's also about remembering the prior inputs and those have impact, right? And kind of making sure you cover things. And the issue is, right, if a combinational component, you can figure out how big its input space is pretty quickly by, multiplying the possibility for each input times all the number of inputs, and then you can get some very large number, but perhaps you can do it exhaustively in some small cases. For a stateful thing, it's a little harder to figure out how big the state space is, right? Because every time you go back in time, there's potentially another, exponent added on. And so exhaust testing is usually out of the question, right? And so do a little more deliberate kind of explore the state space and kind of make sure you cover the things you really care about. And so for this example today, we're going to be using Chisel's queue. One change they made from the prior version on Monday was he said, you know what? We don't need to bother making our own module. We can just use the Chisel module and go with that and make our code a little simpler. So yes, this is just the Chisel standard library queue. Hopefully it works. It's in standard library. Hopefully they've tested it. But let's go ahead and see if we can test it ourselves. So as a reminder, right, the queue, you give it the type you want it to hold. Internally, it's going to have, decoupled input and decoupled output. You can tell how deep the queue is, how many entries it is. And then these extra parameters it has pipe and flow. Flow is a way to bypass the queue if it's empty. If something comes in and goes out in the same cycle without going to register, flow is true, but we made it false. We'll make it easier for us to model this. With the pipe functionality, if the queue is full, it's able to enqueue and dequeue at the same time, right? Because normally, when you're trying to enqueue, you only can enqueue through space, right? If the queue is full, you just say, oh wait, there's no space, I can't do it. However, the pipe is true, you can enqueue because if someone's dequeuing at the same time that you're enqueuing, there will be a space open up at the same time, right? So while you're trying to enqueue, the queue is full. Because someone's dequeuing, you can take advantage of space that can be made, right? Now the reason why it's not on by default is this now creates a connection between queue and enqueue and dequeue, and potentially that's not something you want in your design for either critical path reasons or even combinational loop reasons. And so that's just a parameter we have it on for today. Okay, so we're trying to do a num entries deep queue. How are we going to test this? Well, one of the things I was kind of pitching was, we want to have a way of knowing what's right. And for more complicated components, it's often good to have something that models the functional behavior of what you want, sometimes even the time behavior too, and you can compare against that. So we often call that a model. And in this case, we're going to make a model for a queue. So we're going to use conventional Scala, write a program, and this Scala is going to behave functionally like we want the queue to behave in our hardware. And so to do a queue in Scala, well, there's actually one built in. If you use the immutable version of the collection, you can just, push and pop to it, no problem. However, we're going to actually add some extra stuff to this class to make it look more like a module, right? So we're going to want to make it have, ready and valid and that kind of stuff. And so one of the challenges that comes up when designing these kinds of components, especially with sequential components, is how do you model registers, right? Because when you write programs, you're very used to kind of writing things sequentially and the update order is in that sequence. Hardware, of course, updates happen simultaneously. And so sometimes those semantics aren't well captured by a program if you're not careful. Now, as a veteran programmer, you're probably not realizing you're doing this consciously, but you're probably very adept at ordering statements in a way that makes sense. And we just need to do the same thing when doing hardware. In particular, we need to make sure when registers update, that update happens at a time that makes sense, right? And so remember the semantics of registers are that they only update their value once per cycle, right? Conventional logic, as soon as you change the input, the output changes immediately. For a register, just because you change the input, the output won't change until the next cycle, right? And so the question is, how do you model that? Well, you could have two copies of that register. You could have one variable kind for the input, one variable kind for the output, and then you change the input whenever it gets changed, and then once per cycle you copy the input to the output. Alternatively, if you can guarantee that all the people that read the output do so within a cycle before you change the input, you can update a single variable directly, right? And so that's kind of what's going on here. And so in the case of our queue, we're going to want to enqueue. We're going to want to dequeue before we enqueue, right? And the reason why we're going to do that is that way if we want to do this pipe functionality, we can do that. It'll kind of capture that behavior, right? And also, if we dequeue before we enqueue, that way we prevent the case of someone having almost like flow equals true, in which case, they enqueue and immediately dequeue the same cycle. And so we don't want that behavior today. And so for that reason, we'll make sure we do dequeue before enqueue within a given cycle. And so to do that, we're just going to make sure that whoever calls this model, we want to call this dequeue before we do it. And so how exactly is this implemented? Well, there's ready valid signaling for both the enqueue and the dequeue. So for the dequeue, remember the dequeue is a output, and so ready is actually an input going the opposite direction, so that decoupled bundle back into the module. And so how do we capture the input? Well, we actually make it a var. And the reason why is that multiple things are going to depend on dequeue ready. It's going to depend on impacting both the dequeue as well as that enqueue in the case when things are full. So we're actually going to have somebody who's using this module mutably, this is a var, change this subfield, right? They're going to say, you know what? DQ ready is true now, or DQ ready is false now. We're going to make that up to the model user to do that. For valid, that's an output, right? And saying, hey, do I have anything to DQ? And well, we can simply just see, is the internal queue empty or not? And well, if it's not empty, then yes, I have something to DQ. And then someone's going to call attempt DQ when they're actually trying to get something out of it, right? And well, there's a case of when there is or is not something to return, right? So if there is something to return, that is that not only do we have something in the queue, so DQ is valid, but also the receiver is ready to receive it. This is basically the equivalent to, dot fire, so to speak. Then yes, we should take the thing out of the Scala mutable queue. And you notice here we're using that Scala option functionality. So yes, we have something. Otherwise, we're using none, right? So we're using that to kind of capture the fact that nothing was returned. Moving on to, for example, the enqueue side. Someone asked, well, how do we determine enqueue ready? So enqueue ready is an output produced by that, enqueue port on the module, right? So remember, it says enqueue and dequeue, these two ports on the queue, and they're decoupled, so there's wires going both directions, right? And so when are we ready to receive something? Well, if we have space, of course we're ready to receive, right? And if we're quote unquote full, well, because of that pipe feature, if we're also dequeuing, there will be space, right? Okay, and then what about valid? So valid is an input. As you see in comments here, kind of remind us that if someone calls attempt enqueue, that's kind of implying that they have something valid they want to put in the queue. And what's they going to do? Well, if we're ready, if we actually will take it, we're going to go ahead and receive it. Otherwise, nothing, right? Okay. A lot going on here. We'll pause for questions so far. Or maybe it'll come up when we start seeing how we use this queue model. So for starters, what if we just instantiate a queue model and just see what happens, right? So let's say, for example, we want to push one onto our queue, right? So what are we going to do? Well, we're going to attempt to enqueue one, right? And well, so that's going to say imply that, enqueue is valid, right? These other things are just us kind of checking the fields, right? And so let's see what comes out, right? So because there's room in the queue, for these first three lines, something like, NQ ready. Yes, it's ready to NQ. Is DQ valid? No, DQ is not valid because the queue is currently empty. It's a brand new queue model. And then, someone tried to call attempt DQ. Well, there's nothing in the queue. They're going to get a none. Then this next sequence. Okay, now we're going to say DQ is ready. So it's actually going to DQ something if there's there. And we're also going to try an NQ too. So what's going to happen? Well, NQ is still ready because it's a 2-element queue. We maybe put one in one last cycle, but there's still room. The DQ is valid because something's in there now. And when they tried to attempt DQ, they got that 1 back, right? Okay, so this is kind of a tiny little example. Just kind of showing us kind of calling things very manually. But what if we perhaps use just a touch of automation? And there's a lot of stuff here in the printf, so it'll be more clear when you actually see the output. Okay, so here we're going to do 6 cycles. And what we're going to try and do is on a given cycle, we're going to try and NQ the thing at that value. And we're initially going to not allow it to DQ for the first 3 cycles. And then after that, we'll allow it to DQ. Right? So you can see in the beginning, there's nothing in the queue. So DQ valid is false. We've also said DQ ready by us controlling this thing. We've also set it to false, right? And if you looked at what comes out of DQ bits, it's none, right? There's nothing coming back. And then what about NQing? Well, we are trying to NQ. And it's able, so we're trying with valid and it's ready. And so we're able to do it. And then the data we're trying to NQ is 1. You can see we're NQing cycle number. So 1, 2, 3, 4, 5, 6 is what we're trying to NQ. We're always trying to NQ. Valid is always true. But we can see the readiness changes, right? We have a 2 deep queue. Okay, we can put the first element in. We put the second element in. These aren't being removed. And so on the third cycle, because the queue's full 2 for 2, nothing's being removed, it's full. It can't take any more. Now here, it all of a sudden can NQ again. That's because we started removing things, right? In particular, because that pipe functionality, right? We can NQ and DQ at the same time. And that's why it's able now to continue to NQs or continuing to DQ, right? So you can see that the DQ ready after cycle 3, right, is set to true. Once our queue is not empty, we actually summing 2 DQ. If you look at what actually is getting DQ'd, okay, so we put in 1, we got 1 back. We put in 2, we got 2 back. We're getting 4 back? What's going on? Well, when we tried to NQ3, it didn't succeed. And then we tried to NQ4. So when 4 was NQ'd is when there actually was room. When 3 was attempted to be NQ'd, there wasn't room. So it's kind of a lesson when you have that, producer. If the consumer says they aren't ready to receive, you might need to install internally. So if it was really important to send 1, 2, 3, 4, 5, 6, then the producer should have paused until it was able to do it. But in this case, we're just doing this kind of track where these came from. This is kind of a artificial example. But maybe I'll pause here for any questions. Okay, so we've been kind of getting very familiar with our model. Now what we're going to do is we're actually going to use our model to manually compare. Package test is not a value. Uh-oh, why would it say that? Did I not load in the test at the very beginning? Pretty sure I did. Oops. Oh no, I hadn't apparently. Okay, well, good thing we're doing this. Okay, so let's try and run this code now. Okay. So we're not seeing any output because it's using expect, right? So there's no prints in here. It's just the fact these expects are not triggering assertions means that we're getting the right results. So we can go ahead and make this big again. What are we doing? Well, we have our queue, which is designed in our test. We have our queue model. For this example, we're always going to say we're ready to DQ. So you can kind of see cases here, right? We're going to try to DQ on empty, and you can see there's quite a bit of stuff here. But kind of key things to recognize are that we're calling DQ before NQ. Like I said, that's one thing we have to do for this model. you can see that we're actually capturing from the model that option for dequeuing, and then if there's something supposed to be returned, then we go ahead and expect it. Otherwise, if it's a none, we're just not going to even do it. Okay, and so this example, we try to dequeue an empty, we get empty back, we enqueue a 1, and then we dequeue to 1 and get it back. Okay, it'll be more useful when we actually automate this, right? So how do we automate this interaction? Well, for a given cycle, we're going to say, hey, what are we actually doing? Are we going to try to enqueue? Are we going to try to dequeue? And what data are we doing? As a reminder, these are the fields that are kind of external to the queue. That's why we need them from our test bench. And then the enqueue valid or the dequeue valid, those are going to kind of come from the rest of the world, right? Actually, I'm not sure why I have enqueue ready there. I don't feel like enqueue ready should be. Yeah, it shouldn't be enqueue ready. It should be enqueue valid. Okay, well, I'll fix that afterwards. But now we're able to kind of do a single cycle of kind of a much nicer abstraction, right? So we've kind of worked to tidy things up, and so now we can kind of start building our way up. Right? We built up abstractions. We built up a model. We built up a way to do a single cycle interaction where we're actually having the model interacting with the hardware design. And now when we put these together, we can actually test multiple things, right? So in this case, we're going to push 1 on and then get it back out. And here I added a print line for the queue status of the model, and we can see what's happened functionally, right? But perhaps if we wanted to do an even bigger test, we could try filling for some number of cycles and then draining for some number of cycles, right? So for example, if we wanted to try this out, we get this, right? So we're going to try to fill for until it's full and verify it gets full and then drain it, right? And we can run this for longer, and we can see that behavior. Okay. Before I do a random test, any questions so far? Okay. So then, for the random test, we're going to try and use the same functionality we made before. We're just randomly trying out our fields, right? And yeah, we can see how it kind of fits together. And so yeah, we can test this randomly. We can see in this particular random case, it happened to enqueue these things. If I ran it again because it's random, maybe it ends up enqueuing and dequeuing in a particular order. You can see various things happen. Cool. So yeah, that's an example of testing. We'll come back to testing periodically throughout the quarter. This is kind of a first, 1.2 lectures long primer in the beginning. Cool. Questions on this stuff? Okay. Well, so while we're switching over to the material for today, I did want to make a major announcement, and I kind of deliberately said this in the middle of lectures. That way, hopefully, the maximum attendance. So Campus has informed us that this course will be remaining remote. So I hope that's okay for most folks. So the modality we've developed so far will continue. We'll have Zoom lectures. We'll be still putting recordings online. We will continue to have office hours available on Zoom, as well as instructor feedback via Slack. Support, I should say, via Slack. And also, of course, you can talk to each other via Slack. So hopefully that works out well for folks. I'll be making, an announcement officially, but I just wanted to, get that out. This, came in, late last night from campus. So, it'd be nice to be in person, but of course, circumstances are beyond our control. But I do think this course actually does survive pretty well remote, right? I mean, here we are talking about code all day. Perhaps many of you have these Jupyter notebooks that I'm working with open on your own laptop, and so you're playing the same code I am, etc. The question was, how was the decision process made? I don't believe Canvas, the website, made the choice. The decision process was kind of multifaceted, right? So there's solicitation for myself and the instructor. There's also solicitation from the campus administration, and they kind of went through classes, looking at, how are these classes impacted, benefited, or that are harmed by being remote. And, this class was deemed to be not severely impacted by being remote. And that was part of the decision process. As me, the instructor, I did not actively campaign to keep it in person because I didn't think that was critical for this course. Another classes I've taught, I have pushed strongly to have it in person because I think there's certain in-person things that are really important. But this class, I believe we can do this. So yeah, reach out to me individually if there's anything concerns about this, but hopefully this is okay. And we'll go forward. I'm very happy for all the students who've been in this course so far, and we'd love to hang on to every single one of you if we can. Cool. Okay. Big announcement over. Let's move on to today's content. So we're going to get into functional programming, right? And so for some of you, this may be a very familiar concept. For some of you, you may not have even done it and not even aware what this term means. That's okay, right? We're going to cover this from the beginning. And if you're afraid of this being a very formal, PL kind of thing, remember, I'm an architect that, came from Risk ISA, so I'm a very pragmatic, empirical kind of person. And so really our use of functional programming, to not only today, but in this course is, can we do something that makes our lives easier, right? So in particular, are there language constructs that we can more concisely, more easily, and hopefully more correctly express what we want to get done, right? That's kind of the goal. If it starts becoming overly convoluted and you have to spend 10 minutes to write one line, even though sometimes some functional programming enthusiasts love doing that kind of stuff, that's not what this is about, right? And so we've already learned how to do a lot of things without functional programming. And hopefully by seeing the way we're doing with functional programming today, that'll be so appealing, you'll just choose to do it with functional programming some of the time rather than to be forced into doing it. Okay, so like I said, the PL person might tell you a lot about what it means to be a functional program and all sorts of details. There's a few things to keep in mind, right? So number one, the whole point of functional programming is, yes, it's about tracing data from input to output, perhaps avoiding mutable state are the kind of hallmarks of functional programming. When I say the term in this class, what I'm referring to is actually applying functions to collections of elements, right? That's kind of the key idea, is that we have some group of things and we want to perform some operation on all of them. And that's going to be really helpful for us within our generators, right? Because you can imagine our generators, if they're nice and parameterized, they will do kind of pretty sophisticated things. Some parameter is going to change how many of some widget inside your generator exists, and you're going to want a way to instantiate those and connect those. And we're just going to use functional programming to do that kind of more elegantly, more cleanly. And so as part of doing functional programming, we're going to talk about what's available in Scala. We're going to demonstrate that also in Chisel. In particular for the functional programming in Scala, today we'll be covering map, for each, and zip. That's only a handful of the operators available. There's actually quite a few more. As well, we'll also be talking about something called anomalous functions, or lambdas, so to speak. So let's jump right into it. So yeah, let's go ahead and load up a notebook. Let this kind of complete. Hopefully I don't run out of memory in my computer right now, having two notebooks. Okay, so as I said a while ago, right, why are we doing functional programming? Well, the whole point of this course is to build hardware more efficiently, right? So we're trying to use generators to improve reuse. And as part of building generators, we're often going to have collections of things, right? And so using functional programs that work on these collections, we get some benefits, right? As you'll see, some of these operators, when used appropriately, we can reduce our code complexity in multiple ways, right? So it turns out when we're writing a bunch of loops right now, whether we do for loops or recursion, you've seen us use in these courses to make our generators so far, there's actually some standard patterns, right? So rather than kind of reinvent the wheel each time by writing a for loop in a certain way or writing a recursion in a certain way, we could just capture that pattern with a simple functional programming pattern, right? And so what's nice about using these patterns is that number one is kind of using larger building blocks, so it's fewer blocks to consider, fewer chances for error. It also helps other people read your code if you do it correctly, right? Rather than think about what is this for loop doing, why are they doing this? Oh wait, they're doing a map on this. I know what that is. Okay. And so these are all the pros, right? I can tell you from having read Chisel code for a few years that sometimes functional programming is a great asset. Sometimes people go overboard with it. And I actually am a bit cautious or judicious in my functional programming use to make sure it's actually delivering a readability, code maintainability, correctness benefit, rather than just, flexing your FP muscle. And so one of the things that comes up with functional programming is that normally it's supposed to be side effect free. Chisel, the way it kind of works is very much side effect having, right? We're connecting terms, we're connecting things together, saying, hey, I have this, wire, I'm connected to this, adder, I'm connected this adder to this, register. And so we're deliberately counting on side effects. And so sometimes if you operate on chisel elements with these functional operators, remembering sometimes if you forget these chisel elements are mutable and internally changing, that occasionally there can be a weird situation in there. So you should be mindful of that. But we'll talk about this when those come up. So why this emphasis on collections? If you think about it, most code actually is about collections, right? There's some sort of 80% rule for regular code about like 80% of the time is in like 20% of the rule of code, which is loops or something like that. And it's not too different for hardware, where you may have, if you look at where the hardware resources go in your system, it's often going to be some sort of repeated component rather than one-off logic. And collections are a great way to kind of aggregate these things, right? And so, like I said, we've been using for loops so far. We're going to try and recognize some common patterns and it'll make our life easier. And also, when we kind of use things like this, we actually make the compiler some work to check our compliance with these patterns, or make sure I'm not actually mutating something when I shouldn't or something, for example. So for example, the first two operations we're going to cover are map and for each. So what do? Well, you give it a collection. Let's say here I kind of shown it, abstractly as, inputs a single class instance and happens to have, perhaps n elements of some type inside of it. Who knows what these things are, what this collection even is. It may not be an array, maybe a tree, who knows, right? But given this collection, when we apply a map, we need to give it a function. And that map takes a single element of the input thing, applies the function to it, and produces a single element to the output collection. Right? So if I have n elements of my input collection and I apply a map, I'm going to get n elements of my output collection. And each one's going to have had that function applied to it individually. Now, for each is very similar. That's why I put them on the same slide. We're going to give it an input collection. We're going to tell it these are the function we'll apply to each element. The difference is for each doesn't even have a return, right? So this returns some new collection. For each returns unit. And so you might be saying, well, why the heck are we doing this? Well, because we want the side effects, right? So this function's actually going to have a side effect, and we're going to do this. And so if you're looking at these two things, you're like, wait a second. It seems like map perhaps is more useful, right? Because map returns something. This does not return something. So I could perhaps use map when I meant to use for each and just ignore the output or have this function return nothing. Technically true, but not a fantastic idea, right? And the reason why is that if you know you're not going to return anything, you should use for each, right? So this is kind of a way we can kind of clearly convey this, where when someone's reading your code, they know that, oh wait, this is a for each, so hint, 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 there's going to be a side effect inside here, and that's why they're doing this, right? You could have a side effect in your map, and that's one of the things that really surprise someone reading your code, right? So if you're using map, there shouldn't be a side effect, and instead it should be producing the output, and the output has the desired impact you want from it. And so that's why we have these two things that kind of indicate, well, am I going to produce something new that's going to be somehow a modified copy in some way? Or am I modifying something else, and you should be aware, oh wait, I'm modifying something. And so what's interesting about these particular operators in Scala is that these aren't predefined keywords in the language. Instead, what they are is they actually are methods that are defined on the collections. So when you use the Scala standard library collections, they happen to implement map and for each, right? And due to inheritance, these traits are kind of copied around appropriately, but the key thing is these are actually methods implemented on the collections. So it's really collection centric, and that's why I keep talking about collections so much when I describe all this kind of stuff. Okay, I'm going to pause for any questions here. Okay, so we've talked about those two operations. We're going to need to have a way to specify functions. And although we can name our functions, we're also sometimes going to like to have what's called an anonymous function, right? It's a really small little code snippet that just does what it does. And so in main language, you may have heard these called anonymous functions or perhaps lambdas. In Scala, they're referred to as function literals, right? But basically, it's just a really, really small binding of somehow defining an input and what the output is, right? So in particular, what your syntax is the argument list, this arrow, and then the output, right? And so, the argument list can be multiple parameters, but you give a name and a type. And then the output usually is an expression. If you start finding yourself wanting to have multiple lines, in theory, you could use braces here. Perhaps maybe an anonymous function is not what's for you. Maybe you should do a more conventional function and then you can call it by name. That's fine. So you define an anonymous function. When you declare an anonymous function, it doesn't have to have a name, right? So if I just run the Scala code, this has defined a function that takes an int and produces an int. There's no name to it, right? In this case, I have the same anonymous function. I just bound it to a val, and that's fine. So now if I call inc, I get this reference. Okay, cool. This is kind of the more classic way to define a proper function. Same functionality. You can see if I run both of these functions, they behave similarly. If I want to do multiple arguments, not a problem, right? It takes in 2 ints and produces an int. Okay, so this is how you define an anonymous function. And so with this, we're going to be able to have a code snippet we can use to apply to our collections, right? So now let's go ahead and try out map. So let's say we have a collection and we want to just simply add 1 to every element. Well, so our function could be something as simple as, let's say we're doing it classically, all right, hey, we're taking in an x and we want to return x plus 1, and we're calling this inc. And so how are we going to do this? Well, we're going to have a collection. In this case, let's say L, and L is going to be just using that range notation 0 until 5. Okay, so 0, 1, 2, 3, 4. And we're just going to say, hey, let's call map on it with inc. Great. So you can see originally we have L, 0, 1, 2, 3, 4. And then we map inc to it. We get a new collection. And the result is, of course, those numbers plus 1. 0, 1, 2, 3, 4, 5. Oh, sorry, 1, 2, 3, 4, 5. No 0 anymore. Cool. Now, if you look at the remainder of the output, you might see that these other outputs are all the same result. And so actually, these are other ways of getting the same functionality. So one interesting wrinkle to Scala, and part of why it's so great for using it to make your own domain-specific language within it, this kind of nice feature, is that it has this ability to remove some punctuation sometimes, right? So normally this is the kind of thing you probably used to in most languages. You have an object, you call a method, and you give it arguments. You can put spaces there instead in Scala, and it will just kind of very cleverly, when it's parsing this, recognize what's going on. Okay, I have this object space. Oh, that's a method name that's known to apply to that object. I can do that. And this method's going to need arguments, and so I'm going to go ahead and read what's here next. And so the reason why, of course, they made this is you can make some very nice English readable or English looking like, kind of expressions. It also makes it very natural to write your own new operators in your own language, where if you were perhaps constrained to have everything have this dot kind of syntax, sometimes you couldn't, create things look very native, but now you can sometimes make syntaxes look very kind of nice. And so, for example, if you looked inside of the tests in the homeworks, where it says things like behavior of, and, it should, that's calling, these kinds of things. It's kind of very nice syntax. So I actually do like this ability within Scala. And so I do occasionally, like to have, like an object space, and especially for map. Perhaps this might be my favorite way of expressing this expression is this last line. But to each their own. If you actually read some Scala style guides from industry, some more groups are encouraging to put the extra punctuation in there. They think it just want to be extra clear, extra explicit. Just because, remember, not all of your readers of your code are necessarily experts in the language you've written in, right? So just because someone's reading your code doesn't mean they're a Scala programmer. It could mean they're perhaps a Java programmer or some other programmer. They're just trying to get a gist for what you're doing. And this is why a lot of style guides recommend, doing this anyways, and kind of you're reducing that, any kind of friction, they want to reduce that. And so that's why they recommend against it. So here we are using, the function by name, but hey, let's not even bother doing it. So we could either say, hey, we can call the function ourselves, or we could just, define it inline. So this is kind of the way we're probably going to do it most often, where we're just going to define an anonymous function, i.e. a function literal inline. In this case, we say, hey, we're taking in I, and we're producing I plus 1. If we go back a slide, you can see, we can, here we annotated with a type, But on this next slide, we didn't even bother doing that. We just are counting on type inference, where because this function is going to be applied to this collection is of a certain type, it's going to infer the type for I correctly, hopefully. But maybe if you're worried about that, you could, put something in here to enforce it. Like, oh, wait a second. I thought I was working on floats, and I have to give me an in collection. So sometimes it's good to annotate, but there we go. Okay. Questions so far? So the comment in chat about what the types are in Chisel, and yeah, sometimes in Chisel there's this base type Chisel data that kind of gets used a lot. And so yeah, the type hierarchy for Chisel is another conversation we can have later on in this course. But yeah, types can be powerful, right? It can be a way for us to, capture more of our intent when we're writing our code and let the compiler do more of that checking for us to make sure we didn't make any mistakes. So that was map, and so now we're showing it's its sibling for each, which still applies that function to every element, but the difference, of course, is nothing is returned. And so the reason why you're doing for each is there's some sort of side effect, and this is very good for us to indicate to our readers that the purpose of this operation is a side effect. And so perhaps one very common side effect you may care about is something like printing, right? So what's the side effect of printing? Well, you put something on the console, right? So the console has a certain state, and you've changed that state by, putting characters on it. So yeah, if you, for example, want to print a collection, maybe you will call for each on print, right? Or maybe if you want to put them all in one line, you can, do that, right? But yeah, so we've shown map and for each. And in this case, this is an existing function. We don't need to bother telling it what's going on because the print line can take a single argument. The signature for what's coming out of for each is going to give it a single argument. Those two are going to match up. Okay, so we've introduced map and for each in Scala. So let's go ahead and try them out in Chisel. So as a starting point, we're going to do a couple of things here. This is a very artificial example, but we're just going to kind of minimally show these things applied to Chisel. We can see that really taking these Scala operations and using them in Chisel doesn't require any crazy Chisel, right? So this module is kind of a silly module. It's going to be total number of elements and some constant number, and it's just going to produce, n outputs of that constant. Heaven knows why you'd want this, but it gets the idea across. Okay, so we know how to do, a variable number of ports with a vec. And so what do we need to do? Well, we have so we can do it kind of multiple ways, right? So for the constant output, we can initially have it be a constant output. So for every output, we want to do a side effect, so we're using for each. So for every output, we're going to say, hey, connect that output to a constant of that value, right? Now, if you look at the Verilog for this, hopefully it'll come out. We see, yes, I hear I'm asking for 2 outputs of 8. I get, output 0, 8, output 1, 8. Width inference is automatically inferring the width of these things for us. Cool. Now, perhaps rather than doing a constant number, maybe I want to do a sequence, 0, 1, 2, 3, 4. Well, we can do that kind of nicely now, right? We can say, hey, let's build up a range, and let's turn that range, instead of a range of Scala ints, into a collection of Chisel uints, right? And then we can go ahead and connect those over, right? And so yeah, this is how we could, for example, create a collection of Scala uints. They're not connected to the output, but this kind of shows an example of how we might use them, right? So if you're asking, well, how to connect these to the output, it'll be easier to do that with one more operation we're going to show in just a second called zip. And that's why I'm not doing it right away. And so one very great piece of advice the TA is right now sharing in the chat, I'll put in for the recording, is that when you're playing around these functional programming primitives, sometimes, you get confused, you want to test things out. It's a really good time to take advantage of that, interpreter mode for Scala. So you can go ahead and fire up the REPL. So if you have SBT running, you can type console and that'll launch a REPL in the exact same version of Scala you're running in your project. That's kind of a way I recommend doing it. But if you want to go quicker, you can even just, fire up a notebook and make a new page, or just type Scala in the command line of system works installed, and you can just run that. And yeah, you can go ahead and make some toy examples. You can visualize line by line how these operations work together. It's kind of a great way to kind of see how these functional things are operating. And also, I guess I should also draw attention to the content of the slide, which is pointing out that, as I said, that things like map and for each, those are methods of the collection, and yeah, ChiselVec provides those, right? So here, for example, we're calling for each on io.out, and io.out is actually a output vec, right? So yeah, vec is providing notation of for each, and using object-oriented inheritance, able to inherit that from the right places in the right ways. But that's how it kind of shakes out. Okay, so to recap where we are, we have the ability to make these anonymous functions. We can use map to take something from an input collection and apply function again, output collection, or we can use for each where we kind of want to indicate we're doing a side effect. I strongly, just about require that you not use map when you intend to have side effects. Sometimes there's cases where you want to have like a side effect and return something. Maybe map's not the right way to do that. Like even though the language won't stop you from doing that, just for readability and what you're trying to do, maybe that's not the right way to do it. Maybe you can break it up into a map and a for each, or maybe one pass you produce a new thing, one pass you do the side effects, or maybe another construct's going to be a better fit. But in general, map should have no side effects by programmer choice, not enforced by the language. And for each, the reason why you're doing it is you want the side effects, right? And so it's kind of a good way to kind of declare that intent, make your code more verbose and communicative, right? Imagine if someone just came across the for loop, and the for loop, they're like, well, I don't know if this is going to be just counting things, or is this going to have side effects, not have side effects, producing something. It's not immediately obvious when you just see a for loop, right? But when you see map, oh yeah, someone's producing something, and probably they're not changing anything internally. There's probably no side effects. Likewise, if someone sees for each, you're like, oh wait, I need to be conscious. This is going to have some sort of side effect. And that's why they're doing it, right? So here we are kind of using a little bit richer vocabulary to kind of more clearly convey what we're trying to do for our code, both to the compiler and the humans reading it. So designed for readability. Yeah, another theme. Cool. So another functionality that might be nice is a tuple. So you may see these in other languages, right? Tuple is a way to group together a couple of things. And so a tuple and a seq aren't quite the same thing, right? So sequence is a collection of homogeneous things, and the things have numbered indices. A tuple can be heterogeneous. Interestingly, for whatever reason in Scala, it indexes from 1. I can't explain that, but so normally sequences, you index from 0, 1, 2, 3 with the parentheses. For tuples, you index starting from 1, and you actually do that using a dot, underscore, and then a number. However, you don't always need to use this kind of syntax. Very often you can find it's nice to just create one. It's very natural. Hey, I want to have this tuple 1, and I just want to say it has 2, 3 in it. I didn't create a new type. I just made a tuple that happens to have 2 elements in it that happens to be these 2 things. And hey, later on I can go ahead and even read those elements out separately, and it'll kind of do the right matching already, to kind of force automatically. So what are tuples good for? Well, if you have a handful of things you want to keep together, like I want to have often 2 is the most common, of course. It's kind of to put them together, right? If you start having more things, or it's more, and it's usually it needs to be the place you're creating these tuples, the place you're using these tuples should be very close in code, like a few lines, not the same line. If you start finding yourself having, these pieces of code far away from each other, tuples are kind of a little bit not great, right? Because they aren't very descriptive, right? We're using, dot underscore 1 to find something, right? And so instead, depending on what you're doing, maybe you should use, a case class. You can name fields. Oh yes, I want, dot ID, or I want, dot names. I know what this is. Or if you have a lot of elements, maybe in a homogeneous, you should use a conventional collection, right? And so really Tuples are helpful for when you have the person producing tuples and the person consuming tuples really close together. And rather than creating a whole new type, a whole new case class or something, this kind of moves a lot of extra code, makes it more readable. But I really recommend having these things kind of nearby. I can run this code. You can see the result, of course. Here we declared this tuple, and it even tells you the type signature of tuples, int, comma, int. They can be heterogeneous. So this is, of course, going to be string, comma, int. I can read out the fields with that thing that says over and over again. It starts from 1 for tuples. That's a wrinkle. It's kind of odd. And then you can, of course, kind of extrapolate the values back out. There will be times when we need to use this case keyword. That's part of what's called pattern matching in Scala. I'm not going to go into all details today, but sometimes you can make compiler errors go away. It's kind of being very empirical about this by putting in a case keyword in there. And basically, it's kind of telling it, hey, this is something I want you to match against. In this case, it's kind of doing it on its own, but sometimes you need to give the case, give a little bit of a nudge. And you'll see the example of that in just a slide. Okay, so let's talk about another operation. And maybe I'm going to go ahead one more slide and show you the picture first. So for zip, what are we doing? We're actually going to be given an original collection, a second collection, and that's what we're going to be given, right? So given our original collection and a second collection, what zip's going to do is go element by element and pair them together and create a new collection in which the output is a tuples or pairs of one element from each of the original collections, right? And so if we go ahead and look at this encoding, say, hey, I've, in this case, I'm lazy, so I have a single collection and I'm just zipping with itself. So we want to see what that looks like. We had, 0, 1, 2, 3, 4. If I zip it with itself, okay, well then we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Now what's getting interesting is what if I say, hey, I want to zip up this collection I'm making right now, which is a single element of just 8. Well, if you're trying to zip together collections of different sizes, it's going to allow you to do that, but it's only going to make the output collection the length of the shorter of the two, right? So even though L1 has 5 elements, this other collection has 1 element, and so when I zip them together, I get, a single element out. So it's taking, in order these two collections and putting them together. Now, this last line seems almost like magic. Let's kind of talk about what's going on here. So going left to right using these, perhaps, elided, dots and parens, we're taking L1, we're zipping with L1. So basically we know what that is. We have that up here. So given this, sequence of tuples or pairs really, what are we going to do? Well, we're going to map on it. And our anomalous function is going to take in 2 things and produce 1 thing, right? So in this case, we had to use that case keyword to make it match. And so you can see when it ran, it's going to go ahead and add these things up together. So, 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4. So you see how it kind of did the operation. This is pretty cool, right? So we, in just this, one line of wizardry here, we have a pretty cool result. In this case, we have a zip going into a map. You can often have multiple functional operators on the same line. And this is kind of both the power and where you can get things can get out of hand. So in my experience, I recommend probably having no more than 2 functional operators in a given line. Oftentimes 1 is great, and just having more verbose, val, and kind of anything in between them is great. So a question coming in from chat about how does Scala's zip compare to Python's zip? To be honest, I'm not having good enough memory of Python to tell you the exact nuances, but the first order, I suspect they're quite similar, right? So these concepts of, map, zip, etc., these are not unique to Scala. These are just kind of more general functional programming concepts. And yeah, so Python kind of has many of these kind of built in. And there in Python, they actually are keywords rather than actually being built on the methods. So it's a little bit of a different way of kind of going about that. But yes, you actually can call, map, filter, reduce, zip in Python. And in Python, of course, anomalous functions are called lambda, right? And you can do those. Okay, so why was I so keen to get zip to do that prior example? Well, with zip, it's really helpful for connecting things, right? So in this case, what am I going to do? Well, I'm just going to take an input of numbers, a vector of inputs and a vector of outputs, and whatever those numbers are, we're going to do the absolute value. And so how are we doing absolute value? Well, hey, here's one of those handy Scala functions that returns chisel. It takes in a signed number and, uses mux, right? If it's less than 0, it's going to negate it. And if it's positive, it's going to, convert this true, comma, false in the muxes, right? It's going to leave it alone. And so how are we going to do this operation? Well, think about what we want, right? We have a collection of inputs, collection of outputs, and I have this operation I want to apply to each one. I want to apply this absolute value function to each element. So this is a, perfect example of something that would look like either map or for each, right? And so which one are we using? Well, in this case, we aren't creating a new collection. We're actually just performing a side effect, right? So for each is the right choice here. And it turns out a lot of times that you'll find out that for each actually is quite commonly used in what we're doing in Chisel. So we want to connect the input to the output. So how is this happening? Well, what we're going to do is we're going to take our output vec and we're going to zip that with the input vec. So, output 0 is paired with input 0, output 1 is paired with input 1, etc. And so now that we've zipped those together, we're going to go ahead with our anomalous function here and take those two things and connect them. And in particular, we're going to connect the output to the absolute value to input. And so, so here our little nifty thing has done this. And so, this is kind of a little interesting example of a generator, right? So, sure, I can do, 2 elements, I can do 4, it's parameterized, it's a generator. And then you might say, well, okay, what happens if I didn't have functional programming? Well, knowing what you already know in this course so far, you probably would write this for loop. And I think there's a lot of virtue to this for loop. I wouldn't call this wrong. And guess what? Looking at the output in the Verilog, if you don't have a good memory, it's exactly the same, right? Because the point of what we're doing with all this stuff is that we're using Scala to kind of execute stuff and perform operations, but in terms of what's happening, same number of things being instantiated, same number of things being connected. It's just how is this operation being structured, right? Here, we are structuring it as a iteration on the range of num elements. So it's kind of us trusting that num elements happens to match up with the size of the input vec and the output vec. And then we're kind of indexing each one. So kind of explicitly on each line, indexing to each thing, and then making this connection to the side effect of this for loop. So this for loop's purpose is to have a side effect. Meanwhile, the functional version, you can see that num elements doesn't even appear here, right? Because we aren't counting on that parameter. The parameter set up the bundle size, and now we are just taking whatever the collection has, right? So io.out, has, fortunately because of up here, num elements, and we can go ahead and zip those together with the input elements, and now we have this, collection of tuples, right? And we can do functional programming. So you can see kind of a head-to-head comparison. Maybe this one's too artificial, too small, so maybe the benefit doesn't seem too huge, but we'll start showing more examples in the coming slides. I'll pause at this point if there's any questions, however. Okay, so with the anomalous function, there's one little detail that you may have seen already inadvertently, and I kind of talked about. I'm going to talk about again more in more detail. It's something called a function placeholder. It's kind of the terminology used in the Scala language, right? And so when you're making these anomalous functions, these function literals, you can make them super, super concise by using an underscore. So underscore is kind of like this magic wildcard. So how does it work? Well, normally when you do a function literal, you have to give it inputs, arrow, outputs, right? But you see I here twice, maybe that's too much. So instead, you can use this placeholder. And so how it works is that every time you invoke a placeholder, is a single use of the argument. So in this case, there's a single argument, I have a single placeholder. If there's a scenario where I want to have 2 arguments and I use the placeholder twice, the first time the placeholder is going to use, it's going to use the first argument. The second time the placeholder is used, it's going to be the second argument. And so if you want to use, for example, the same variable twice in your function on the right or something, you can't do it with a placeholder. You should properly name it and such. And so Usually things that use placeholders are very trivial expressions. That's why we're using this to kind of make it concise and even faster to read and parse. If your expression starts getting more complicated and you still have placeholders in there, that's probably not good for readability. You should definitely, as it says here, you can give explicit names to all of your arguments to your function, right? So, and going back to our incrementing example, you can just say, hey, take the element that we're given and add 1 to it. So it's kind of a very nice syntax. But like I said, these things, if used judiciously, are great, but can easily be overused and hinder readability and also the ability to get correct code and debug. And so, yeah, be a little cautious at times. Cool. So if you remember back to last week, we talked about an arbiter. And we had this example arbiter, and we showed you how to implement it a couple of ways. This was the second of the 2 ways we showed you how to build it, where we generated this list of 1-hots and then used them to kind of perform all the operations we needed. So as a reminder, right, our arbiter takes in, n, or just say numports, decoupled inputs, right? They all perhaps make requests, and only one's going to come out the other end. And we need to let the requesters know via ready valid signaling that they succeeded, right? So these requesters, they are sending a valid indicating that they're trying to make a request, right? And this component's going to respond with a ready to let them know that they actually won, right? So even though there's going to be, there's numports, ready signals and numports, valid signals in here, right? So remember how we handled this was, well, we declared some wires that kind of pre-declare our variables, and then we had this for that kind of went through and connected a lot of things, and we kind of put it all together, right? So remembering what we're doing, well, these operations we're applying to every single port, right? We want to, for example, have the return path be if that one was chosen and, we're firing, right? Something's happening at all, right? We also, of course, want to collect all of these valid signals on the input wires, right? So we're going to go ahead and in our for loop kind of keep connecting all these to this wire vec. Additionally, we don't want the data vec, and so we're going to go ahead and collect those as well. So these two are really just kind of gathering fields for us, right? Right now it's kind of all buried inside this vec of bundles, right? And we're trying to grab those fields out into a vec of just those fields. And then with just those fields, we can do things like, in this case, we want to do a reduction. We want to find out if any of those bits is true, right? Or in the case of this other one, we're going to use this to, pass this into a mux that's going to select it. So lecture 8's the way we covered this component originally, if you remember how that kind of fits together, but most of them is showing this to kind of remind us how we did this. And, this is pretty solid code, right? But it's actually kind of a little bit hard to read, right? It's kind of a lot of mutation here. I kind of remember, okay, I'm connecting one side of these wire vecs up here and then using them later on. This for loop. Could we tie this up with functional programming, right? Yes, that's why we're doing this. So let's talk about the valids first. So before we wanted to collect the valids, we had to declare our wire vec, and then we had a loop, and then we connected them one by one. With functional programming, we can say, hey, you know what? We want just the valids. So I'm going to take that collection of ports. In this case, I want a map. I actually want to return something. And for each one of those ports, using that placeholder syntax, give me its .valid field. So, what was potentially, 3 lines in the prior last slide, we had the declaration, the for loop, the connections. Now we're talking just a single map call. So that's pretty cool, right? And this is really nice, simple code, right? This is, there's no mutation going on here, right? This is, nice access to a collection. We don't need to remember that IOREC is numports long. Just by virtue of having a collection here is kind of implicit and it's handled for us automatically. This is kind of nice, straightforward, simple stuff. And for example, when we wanted to do the reduction, reduction is kind of the same, right? Here they, cast it as a uint.or. I perhaps could do the same thing to make this even simpler. Let's see if that still compiles. Oh, and the reason why, of course, is it was not a vec anymore because of the map call. So it's good we did this to remind myself why I did that. So after we did the map, we had a vec, but now returned a Scala collection. We need to, once again, recast that as a vet collection. That's why we needed to do that. It just seems extra odd. It's only because we're doing this dot as you went OR reduction. You don't do OR reduction every project, so it's okay. But continuing through the other lines. Okay, so what else do we have to do? Well, we had to do all this work about, choosing one hot. And so it chosen one hot. Well, we did a priority encoder on the invalids. How's it happen over here? That's exactly the same thing. We just do a priority encoder on the invalids, which we gather together nicely with this map command. Now, what about the output bits? Well, remember we, originally had to kind of go find those bits by, doing another one of these gathers where we had, we declared a wire vec. We went through a for loop and connect everyone, and then we passed them over here. To kind of really show the functional programming really taken to 11, we're doing that gather with the functional programming like we did up here. But now we're even naming that, right? We're just putting it in there directly, right? Because it's so compact, it's perhaps not egregious to put that in there. Maybe sometimes for style and readability, maybe you should, take the time to give it a val and a name. But in this example, we put it that way to make sure you kind of see that, this is, concise and you can really kind of get things going. And then for the grand finale, let's talk about how we're going to go ahead and rewire up the readies, right? So remember the readies over here. What we had to do is we had to reach one of these readies. We had to connect it to not only the result of the one hot choosing by the priority encoder, but also if that port was, also if the general output was firing. That's kind of something we were concerned about. So if we go, I can make this double to make it consistent. How are we doing that here? Well, we're just taking our input ports, zipping them with those chosen one hots, right? And now that we have, the input port and the chosen one hot, then we're now going ahead and working on these, right? And once again, this one's having a side effect, that's the whole point. So it's going to be for each, right? So see in this tiny example here, we have both map and for each, right? When we want the result, when we want the side effect, right? It's kind of be very distinct about the two. And yeah, you can see we're applying that thing to it right here. So we're doing that whole functionality, which in the prior slide was, accomplished by multiple actions. We had to kind of have a for loop and write this all out and take advantage of the ability to index. Now we're just doing that with the functional constructs. So cool. You can see this thing is, just by line count, substantially shorter than the prior slide. But hopefully it's also just simpler, right? Now, like I said, functional programming can be taken too far. You can make things that are too complicated, too tricky, hard to read, hard to modify. And yeah, you should be cautious of that. However, I think in this course, especially for some of these homeworks and some of these labs, if you haven't done a lot of this before, try it out, right? Maybe try to go far into functional and see what works, what doesn't work, and what's too far, and then you can kind of scale it back, right? Because yeah, a lot of times we have assignments in this course, there's kind of nice, compact little problems, and so yeah, they're a great place to kind of try out and experiment. Cool. Any other questions? Cool. Well, with that, we'll sign off. Have a good day, folks.